Good morning, ma'am.
Yes. Today I'll continue from the second class because I left some portions, I mean the examples of mul instruction, how we are comparing with the risk and CISC. Then later in this subject, we are discussing with the risk machine, okay, and we are discussing the ARM processor. So in the first class, just we were discussing about the introduction of the subject. So in the previous class, we're discussing about introduction to the microprocessor, and mainly we are using two types of the microprocessor, RISC machine and the CISC machine. Okay, and we have seen the difference between CISC and RISC. Once again, I want to explain the example. How the operations will be there, risk and CISC, but obviously here we are using both the machines. Here nowadays we are using advanced risk machines. Just we'll go to the slide, the second class slide. I'll finish, then we'll go to the third class. So now in this case, just we have taken an example for risk versus CISC machine. So consider the program fragment here. So A equal to B into C. So I mean B and C is multiplied and the result will be stored in A. And we have some values 10 and 5 which are assigned to B and C. So how we are executing the program? First we need to initialize the value 5 to C and 10 to B. So for that in the assembly language we are using the instructions load instruction. And we are loading the value to the memory locations. Again from the memory location, after the result we will load back, I mean we are using store instruction. So after loading the values, then we use add B and C, or in this case multiply. In generally it is mul B and C. Store the result A back to memory location. So now what is a CISC here? Okay, so CISC is a complex instruction set computer and RISC is a reducer instruction set computer. So this is the example for the CISC. The same example instead of program 1, I'll take the program 2 where we are moving the values 10 and 5 to the AX and BX and mul instruction, and I'll take the program 2 for the comparison of the risk machine. The same example is there in the risk machine as see the what is the instruction here, A equal to B into C. So that is in the high level language. If you are writing into the machine level language, as in the risk machine, this is just one example. Here it is a risk machine, risk processor. Either it can be 8085 or it can be 8086 or it can be ARM processor, whatever it is. This is just example. Okay, so we are not discussing with respect discussing with not any the architecture, just simpler example. See now one thing here we need to see, Cx comma phi is used as a counter because we are not using Cx directly here. So isn't it? So you can see Cx is not using directly anywhere. Okay. So first we are assigning value Ax to 0, Bx to 10. Then move Cx comma phi. Assume Cx is that architecture is it's a built-in architecture. Maybe it is in 85 or it is 8086 processors. So now we are begin the loop. So now instead of mul instruction, I am using add instruction here. Okay, because mul is a complex instruction which can be take more number of the cycles for the execution. Instead of that, I am using simple instruction as AX and BX. And you know what is a multiplication instruction and the addition instructions we have discussed in the digital class. Okay, how the multiplication works and how the and what is the circuit design of the multiplication also. So it may take many number of the clock cycles. Instead of that, I am using add instruction. So now add AX and BX in the loop 1, the value will be 10. I mean A equal to 10. I am adding B 10 to A. Initially A is 0. So now loop begin. So before the loop we have a counter here. Okay, so assume we have a counter here. So now the counter starts from 5 when it becomes 0. Either it is in incrementing or decrementing. Just assume this is a counter. So whenever the counter ends, so the loop has to start. Then it has to come out from the loop and it will start. It will start executing the next instruction. So like that we are executing 5 loops here. After 5 loops, 10 plus 10 plus 10, each time 10 is going to add it to the previous value. So the result will be 50. So now you can see here the number of instructions are more in the RISC machines, but where the number of instructions are very less in the CISC machines. Okay. So in the CISC machines, the number of instructions are very less. So either it is one instruction or 3 instruction, but I have taken for 3 instruction. So see the program 2, we have 2 move instruction and 1 mull instruction. But the same thing in the RISC machine, we have 3 move instruction and 1 add instruction, 1 loop instruction. But here the loop is executing 5 times, so we'll take 5 add instruction and 5 loops. So we'll compare the time here, how many cycles we required. The total clock cycles for the CISC version is 2 move instruction into 1 clock cycle. 1 mull instruction we'll consider as 30 cycles, so it is 32 cycles. But the same thing for the RISC machine, even though if you're having more number of the instruction, then we have 3 move instruction into 1 cycle and 5 add into 1 cycle, but 5 loop. 5 and again the 5 loops into 1 cycle. Everything is 1 cycle only. But compared to the mull instruction, see mull instruction, 1 mull instruction takes 30 cycles. So in the RISC machine we'll get 13 cycles. So with the RISC clock cycle being shorter, that means the RISC gives us much faster execution speed. But nowadays we are using CISC as well as RISC machine. So we'll compare the RISC and CISC here. Okay. So the RISC are the simple instruction, few in number. I mean instruction set will be having few instruction. CISC many complex instructions like mul, die, so. And in the RISC fixed length instruction, CISC variable length instruction. So I mean the CISC RISC fixed length means suppose if I use any one specific processor, either the processor is having only the 3-byte instruction or the processor is having only the 4-byte instruction. But in the CISC machine, suppose if I take any one processor, variable set instruction, either I can have 1-byte instruction format or I can 2-byte or I can 3-byte. So it is a variable length instructions. And multiple register sets will be there here. Single register set, 3 operands per instruction, 1 or 2 register operands per instruction. So the parameter passing through register windows, parameter passing through the memory. Here we have a single cycle instruction. I mean for one instruction 1 cycle. For multi-cycle means for one instruction multiple cycles will be there. Okay. So we have hardwired control and it is a micro-programmed control, highly pipelined. RISC machines, CISC machines are less pipelined. So RISC uses only load store instruction to access the memory. Suppose if you want to access the value from the memory, I mean if you want to assign the memory, assign the values to the register, it has to use load store instruction. Directly it cannot access the memory. But in the CISC machine, many instruction can access the memory. So for example, here I have used mull instruction, isn't it? Mull instruction AX, BX, CX. Now see, there is no load store instruction. That means some of the instruction can directly access the memory values. But in this case, for RISC, I have to use load instruction, load the value to A, load the value to B, then use the operation. In the RISC machine, we have very few addressing modes. In the CISC, we have many addressing modes. These are all the difference between, or just we are comparing RISC versus CISC machines. So the next, anyway, we have two types of the processor here. I hope it is audible.
Yes, ma'am.
Yes. And what are the RISC and CISC machines today? So we are using many of the processors. Okay, many of the devices we are using. We are using laptops, we are using smartphones, and we are using home appliances, and as in that now all internet things, IoT things we are using. So we are using both the type of the machines today. So we are, as in we are comparing the efficiency, or it is a less power, or it is a high speed, whatever it is. But both the processor we are using for different things. So with the rise of the embedded systems and the mobile computing, where it is increasing, the embedded systems and the mobile computing are increasing in the world, the terms RISC and CISC have lost their significance here. I mean, here we are not preferring only the RISC machines. We are not preferring only the CISC machines. Nowadays, memory is not a matter, isn't it? We will be having in the form of terabytes here. So we won't, even if it takes lot of memory also, I need the time here. So the time efficiency I need. Okay. So we have to see how fast it executes. Okay. So like that, some appliances, some can be used for RISC and some can be used for CISC. So as in the case, we cannot differentiate much here RISC versus CISC machines. And we have advanced RISC machines, where which is having somewhat equivalent to the CISC machines. Both architecture almost seem to have adopted the strategy of the other nowadays. Some RISC systems provide more extravagant instruction sets than some CISC systems. And the CISC chips are now able to execute more than one instruction within a single clock, including the pipelining here. So the pipelining is a very interesting topic here actually. We will discuss the pipelining, either it is a 3-stage pipelining, what is a 5-stage pipelining, how the pipelining for one instruction. Okay, so that's very interesting. And the RISC versus the CISC debate started when chip area and processor design complexity were issues. Now, anyway, the energy and power are the issues. We don't mind about the memory here. We have a lot of memory here. We'll get the lot of memories here. The two top competitions today are ARM and Intel processor, where ARM is a RISC machine and Intel is a CISC machine. Intel focuses on performance and ARM focuses on efficiency. So ARM is from the British company known as Advanced RISC Machine. So now some of the architectures. So we have Intel Pentium 4, Core i7, AMD, and IBM processors. Okay, XIFX, Spark architectures. Spark 64 is some Spark architectures. We have many architectures actually. Under RISC and under CISC, we have different architectures. So we are preferring for our subject, we are going to discuss with the ARM processor, where ARM is a reduced instruction RISC machine, or it is a advanced RISC machines. Okay, advanced RISC machines. So in the next class, the next we need to discuss about the ARM processor. What is the ARM architecture? What is the design philosophy of the ARM architecture? Okay. So now there are number of physical features that have driven the ARM processor designs. First, portable embedded systems require some form of the battery power. ARM processor has been specifically designed to be small and reduce the power consumption and extend the battery operations. Usually these can be essential for the applications such as mobile phones and the personal digital assistants like PDA is what we were using in the earlier. And also in the ARM processor, high code density is a major requirement because ARM processors are used with the embedded systems. Embedded systems have limited memory due to cost and or physical size restriction. And this high code density is useful for applications that have limited onboard memory, I mean, such as mobile phones and the mass storage devices, etc. So ARM core is not the RISC architecture because of the constraint. I mean, not pure RISC architecture. It is an advanced RISC architecture because of the constraint of its primary application. The primary application of the ARM processor is a embedded system. Okay, so I mean the strength of the ARM core is that it does not take the RISC concept too far. So I mean in today's systems, the key is not raw processor speed but the total effective system performance and the power consumptions. Okay. So now we need to discuss in the coming classes in the next lecture videos, source video, we will discuss about the ARM processors. So now in between just I'll stop and I'll explain if you want. So now in this class, in the MPC classes, sir is going to explain about the ARM processor architecture. So what are the different processor modes we are using, different instructions, data type, and we are discussing the in our microprocessor architecture. We are discussing the ARM processor architecture, the what are the instruction type of the instruction, length of the instruction, so on those.
One, the ARM architecture. Then we'll try to understand the different modes at which the ARM processor work before architecture, the ARM processor, the ARM processor. Here we'll understand the ARM processor, terminology and its applications. We'll have an overview of the ARM architecture. Then we'll try to understand the different modes at which the ARM processor work before going in depth of the architecture part of the ARM processor. So what is an ARM processor? As we discussed in the previous session, ARM is a RISC machine, reduced instruction set computer. A stands for Acron or Advanced RISC Machine. It is called Advanced RISC Machine because it incorporates lot of good features which are in CISC machine. Due to advancement in the technology because of the processor speed, few complex instructions like multiplications are incorporated here so that users can write program in the sophisticated manner. Coming to the technical specifications, it's a 32-bit embedded processor nowadays, which occupies 75% of the market. Basically, they are high performance processor which consume less power. More importantly, they cost less. Since they cost less, lot of manufacturers like mobile manufacturers or any embedded applications uses ARM processor instead of going for the costly processors like Intel Atom processor, which I told you in the previous session. It has provided solution for lot of real-time applications, industrial and network applications, mobile applications, which can run on any type of operating systems, including your Android OS, which you use in your tablet or in your mobile phones. That is the background of your ARM processor. just to convince ourselves that ARM is
See, one thing why we are studying the ARM processors here, okay? The ARM processors are found in numerous market segments. So it is including networking, automotive, mobile and consumer devices also, mass storage and imaging. Within each segment, ARM processors can be found in multiple applications. Okay. So for example, the ARM processor is found in networking applications like home gateways, DSL modems for high-speed internet communications, and 802.11 you'll be learning in network, computer network, wireless communication, and the mobile device segment is the largest application area for the ARM processors because of the mobile phones. ARM processors are also found in mass storage devices such as hard drives and imaging products such as inkjet printers, applications that are cost sensitive and high volume. But in contrast to the ARM processor, not found in the applications that require leading edge high performance, because here these high performance applications tend to be low volume and high cost. ARM has decided not to focus design on these types of the applications. So as in the summary here, pure risk is aimed at high performance, but ARM uses the modified risk design philosophy that also targets good code density and low power consumption. An embedded system consists of a processor core surrounded by caches, memory, and the peripherals. So the system is controlled by operating system software that manages the application tasks.
widely used. Since we are studying this ARM processor in detail, we need to realize ourselves that yes, ARM's processor is used in all the applications which are familiar to us in the market, whether it is the mobile applications or the devices which can run the mechanical softwares, Linux operating system, whatnot. So many things can be built on the ARM processor. Basically, ARM is not ARM industry. They don't manufacture or they don't fabricate the processor. They provide the core and they provide the license. So based on the application, based on the device, whether it is a TV or mobile phone, based on the size, the fabricators can devise the processor of their need. They don't come with the fabrication. They get the core on which they can build. But the core is same, that is instruction set is same. So the programming for all these devices will be same. So once you learn any ARM processor, you can code for any devices which are listed here. This may create few more interest because most of the mobile phones, whatever is shown here, maybe they are the old devices. But yes, any new devices you see in the market, they use the ARM processor instead of going for Intel processor, which are costly in nature. Yeah, many student hackathon projects use these two programming boards, Raspberry Pi and Arduino boards are used. The Raspberry Pi and the Arduino board, they use the ARM processor. You can see here, I have just marked in the red color arrow, which is pointing to the ARM processor. One board is the Arduino board, which is in blue color. The green color board is the Raspberry Pi. Most of the student project in the academics, they use these two boards, which has the ARM processor embedded into it. Right. So learning the ARM processor make a lot of sense for us. So just these are all the motivating points to learn the ARM processor. Few projects which really we can feel that we know this type of project, whether it is a robot application which use the GPS technology, any inquiry system which is built in the hospitals, the system which can be used for checking the temperature or the humidity in the farmland or in the uh, restricted areas like hospital medicine storage department, those type of places. If you want to devise a simple device, it can be built using the ARM processors, vehicle tracking system, biometric fingerprinting system, the automated bus arrival or the metro train arrival system for blind people, any digital notice board which you see in the academics can be built using the ARM processor. So learning the ARM processor make a lot of sense. So here we have decided to teach programming the ARM processor. Right. So what is available in the market? We have different versions of ARM processor, starting with the version 1, ARM 1 with the 26-bit, and from the from the ARM 2, we have 32-bit processor. Previously, we did not have the multiply instructions which were embedded in the ARM2 processors. Then ARM, okay, ARM 9, strong ARM and ARM 9, they were able to work on the off word, that is 32-bit if you consider as single word. Off word is 16. So in order to reduce the code density, like as I told you, devices will be small. You can design any big devices or the small devices. If you want to reduce the code density on the device, instead of programming for 32-bit, you can program for 16-bit. So few versions like 4T, they provide thumb operations which you can use it where you can write program for 16-bit instruction instead of going for 32-bit instructions. Like so, nowadays you get Cortex M, Cortex R, and Cortex A Neo versions in your mobile phones or the tablet. If you want to understand more on the versions, I've given the reference here. You can go through the reference in the internet and you can understand different versions. But what we study here is the ARM7 TDMI processor. It's a 32-bit processor.
So in the previous slides are explains what are the different ARM processors. See, we have different processor, main processor like CISC and RISC machines. In that we are going to study the ARM processor, but in the ARM itself we have several type of the several versions of the processors. But in our study we are using ARM7. Okay, ARM7 TDMI processor.
Which support thumb operations, where T stand for thumb in the TDMI. That means that you can write 16-bit program as well. D stand for debugging support. M stand for multiple enhanced multiplier. So you can, if you multiply two 32-bit instruction, if the result is 64-bit, it can accommodate. So it can accommodate the 64-bit multiplication. So how it can be done, we can write the program and we can see. So I stand for embedded IC hardware, which is of which will not be exploring much, but T and M part will be exploring more, right? So again, in general, it follow the von Neumann architecture, stored memory architecture, where we use load and store operation for doing the memory reference, and it's a three-stage pipeline processor. When it comes to the pipeline,
And also, ARM is a load store architecture. Okay, so ARM is a, you may get the questions here for this. ARM is a load and store architecture. Why? What is the load and store architecture? Because to, for example, A equal to 10, B equal to 5. If you want to assign the values, we used to use for the memory locations, we are using load and store architecture. Okay, so that's why it is a load store architecture. We used to call load and store architecture.
in the second unit, we go for five-stage. We learn five-stage pipeline, so we'll not be using the ARM there. But yes, ARM, as specified, since it is a RISC processor, they follow. They provide a three-stage pipeline. That means that you can execute three instruction at a time. So when we learn the pipeline processor, we'll understand what it means. Now, looking at the block diagram of the ARM processor, as I told you, the processor is a three-stage pipeline processor which has fetch, decode, and execute, which is slides. The operation is slides to fetch, decode, and execute. We'll look into this in detail in the third unit. Though it is a three-stage pipeline processor, if you write a non-pipelined operation, if you want to perform, you can perform. You'll not realize when you exactly write the code whether your instruction is working, executing in the pipeline fashion or the non-pipelined fashion. Coming to the specifications, all the buses are 32-bit. That means the data which you can the data which you can work on is the 32-bit data. Of course, you can work on the 16-bit data also. That is your and the instruction 32-bit, 16-bit instruction in the thumb mode. Address bus also is 32-bit, and you have a register bank. You can see here. There is a register bank. It is not only the register set, which we call generally in other processor, we have the register bank. We have 37 registers, which are of 32-bit size. In the next session, we'll talk about this 37 32-bit register. But you need to understand that we have the register bank. Why we need the register bank? What is the use of register bank? We'll understand later. And the more important is that this ARM processor has a multiplier 32 into 8. Both multiplication can be done here. So you have a multiply instruction which can be used to write the program. Then there is a barrel shifter. So the input to the ALU, you can see one input is directly coming from the register. Another input is going through the barrel shifter. So this makes a lot of sense when we write the program. When we look at the instruction set, you will understand how the instruction accommodate this shifting operation also, whether it is mandatory or the optional thing. We'll look into it when we look at the instruction, right? So in nutshell, this is the block diagram of the ARM processor, which are required for us to write the program for this processor, right? So next, so whenever we are writing the program here, the word means it's a 32-bit that is 4 bytes. So byte is 8 bit. It is known to you. Half word means 16 bit. That is 2 byte. As I told you, it's a TDMI processor. So I can write the program with the 32-bit instruction or the 16-bit instruction. Again, I repeat, 16-bit programming need to be done in order to reduce the density on the smaller devices. If at all that is the requirement, you can write the program with the less density program. Okay, so coming to the data type, ARM processor has 6 data type. One is 8-bit signed and unsigned. 2 here 8-bit data. Then you can have a 16-bit data, that is half word. Again, it can be signed or unsigned. Then of course the 32-bit signed and unsigned data, which tells that aligned to for 4-byte boundary. That means that memory will be of 4-byte. Sorry, memory will be a byte, right? So in the memory, you should have 4 bytes to accommodate 32-bit data, right? So this data can be in the Little Indian or in the Big Indian format, right? So you need to brush up the Little Indian and the Big Indian formats to understand this boundary thing, which we can discuss offline also. Yeah, so coming to the mode, the processor, ARM processor work on 7 different modes. Mode here is to tell that what program is being executed on the processor. Normally, we assume that only user program execute.
See, the processor modes are very important here. So why we are using the processor modes? The processor mode determines which registers are active, because we have several registers here, okay, and not all the registers are active at a time, and the register, some of the registers are active at the particular mode. So the processor mode determines which registers are active and the access rights to the CPSR register itself. Okay, so each processor mode is either privileged or it is a non-privileged. Okay, so the privileged mode allows full read-write access to the CPSR, which we are going to discuss later, and the non-privileged mode only allows read access to the control field in the CPSR, but still allows read-write access to the condition flags. So we will discuss all these modes.
Put on the processor. No. On the processor, user program will be executing, but when it comes to the maintenance, when it comes to error handling, user program may be removed from the processor and the system program may execute. The system program come for execution with the high priority or with the low priority, or to abort the processor, or to do the undefined instructions, and there can be some system operations which need to be executed. We'll discuss this in later, right? Other than the user program, other modes are called privileged mode. So these are all the program which are system specific. Whenever they want to execute, user program will be removed from the processor and they go for execution. So user program will be the low priority program. If nobody is there for execution, user program can execute. if any priority program, whether it is in the supervisor mode, abort mode, undefined mode, or the system mode, or the interrupt mode, interrupt handling situations, whether high priority or the low priority, user program will be removed from the processor for execution, right? So what exactly you mean by this? What happens when program is executing? When program is executing, and we expect the program should complete its execution, or execution may be halted temporarily or permanently. Permanently means it is aborting. I don't want to execute your program. I'm going to remove you from the execution and it will send it back to the memory for different reason. The user program may be halted temporarily. That means wherever you are executing, in between they will stop and the privileged program can come for execution. Once the privileged program completes its execution, user program can resume its execution. That's the meaning of halting the program temporarily. Why user program execution will be halted temporarily? User program will be halted temporarily because some other user program like functions or subroutine need to be executed, or operating system want to perform few maintenance work. So obviously you need to go to the privileged mode and operating system, uh, some program which are related to operating system will execute. Or error handling. There can be a interrupt. Interrupt are nothing but these signals which can be generated by the hardware or by the software in order to tell that there is some urgent work need to be executed. Maybe the error handling itself, or cleaning up the memory, um, or anything like some uninterrupted, unexpected uh, error has happened that need to be rectified, which is more important than executing the user program. So that time your program may be temporarily halted and the uh, error handling programs may execute before the user program, right? So what happens when user program is executing? Some important points which you need to remember. I'm just summarizing whatever I told till now. User program will have the lowest priority. Context switching takes place. That means that shift from user program to the privileged program will take when system program want to execute. So as I showed you previously, system program can be low priority or the high priority. If the low priority program is executing, if high priority program comes for execution, then the low priority program will be removed and it will be high priority program will be given chance for execution, right? So removed means context switching. The context at which user program is executing is shifted to privileged mode, either whether it can be lowest priority or the highest priority uh, mode it will enter. So whenever there is a context switch, I'm executing my program, I'm leaving my execution in between, I'm going out for execution. So I need to save all my data, temporary, whatever I have in some place, so that when I resume my execution, I'll start execution from the point where I stop the execution, not from the beginning. So I need to store the temporary data someplace. So how it will be done is what we are going to learn in the next session when we learn about the register, right? So just to summarize the process, whatever I told, the context about the context switching. So I have a processor and I have three user program in line. for execution. This is called the queue. I have 3 programs in the queue for execution, which is waiting for CPU time for execution. When program 1 goes for execution, program 2 and 3 will be waiting for execution, or it will be waiting for program 1 to complete, or it can be processor time can be given in the uh, rotation basis by the scheduler which you are going to study in the operating system course, how the scheduler will schedule the processor time for different user program. So when user program 1 completes execution, or time is elapsed, user program 2 will come for execution. If user program 1 complete the execution, it will go out, otherwise it will go back to the queue waiting for the second chance. When user program 2 completes, user program 3 come for execution. So there is a context switching taking place between the user program itself. Now when user program 3 is executing, I have a priority program came for execution. It has arrived for execution when user 3 program is executing. So wherever the execution, whatever may be the point of execution.
See, a priority program means some interruption occurs. Suppose if I am executing, user program means if I am executing my program, user is executing the program, suddenly some service has to occur. I mean, some interruption came, either it is any of the system, so service has to be given from the system actually immediately. Then our program is going to interrupt and it will go to the interrupt service routine. So that is known as a priority program. So priority program, user program is not the high priority here.
There will be a context switch between the user program 3 and the priority program. So priority program will go for execution and the user program 3 will go to the waiting queue and it will be waiting for its chance to execute. When priority program 1 is executing, at the same time, if one more priority program of the same priority what priority program 1 is has arrived, another high priority program also has arrived at the same time. So user program also is waiting, low priority program also is waiting, and the high priority program also is waiting. Now there will be a context switch between the low priority program and the high priority program. So different mode. So at one time I was in the high priority mode. Once I was in the user mode, and once I was in the low priority mode. So how the context switch takes place? What will happen during the context switch? How the register or the register bank come into picture during this context switching? What is the significance of the register bank, which I just showed you in the block diagram? We'll understand when we study the register bank in the next session. So do remember the terminology of context switching, the interrupt, and the significance of low priority, high priority, and the user programs, right? User programs are always the low priority. If I don't have any other program for execution, then only user program will be given chance for execution. So now we can understand the different modes. User mode, very unprivileged mode. FIQ mode, very high priority mode. Whenever there is an interrupt raised by the hardware or the software, uh, there will be a shift from user mode to frequent priority mode. IRQ is the low priority mode. If the user program is executing, if IRQ come for execution, then user program will give chance to low priority program. If low priority program is executing and the high priority program come for execution, then the low priority program will give chance to higher priority program. if the higher priority program is executing, at the same time user program or the low priority program come for execution, then high priority program will not give chance for user program or the low priority program. High priority program will continue its execution, right? This is one view you should have when you are understanding the mode. So we have, similarly, we have supervisor mode, abort mode. Abort mode, interrupt will be raised or there is a change if I want to clean up the memory or if I want to do some memory management program. So I'll go to abort mode, and there is a undefined mode like the program which I'm executing. Most of the instructions I am familiar. There can be a new instruction which may be from the older version or the new version of the processor, which I'm not aware. So I should go back and I should understand what is the undefined instruction, and I should come back. Once I understood, I should come back and I should execute. If I don't understand, I should tell that I cannot execute this. So I need to go to that mode for execution. The supervisor mode, yes, which is used, which it will, my processor will enter if I want to reset or abort some operations, right? So we'll discuss about this modes with respect to register bank. What are the registers which are used in different modes in the next session. So with that, we'll
Ma'am?
Hello.
Ma'am, could you explain that supervisor mode?
Supervisor mode. Okay. Okay. Yeah. And other things, can you send me a message? Because already 10:07. At least you need some 8 minutes break. Okay. So message me and any other doubts. Okay. So next at the starting itself, we'll clear the doubts. Okay. Yes.
Yes, ma'am.
Okay. Supervise mode. Okay.